And I will make this one other announcement before we do get actually started. And Nigel's here. Okay. Let me lead with this. Even though this is one of my best classes as far as getting papers in, meaning 33% have gotten them in, okay, that's still a pretty low percentage, especially since we're running out of term. So don't forget, and you got a week coming up, Thanksgiving week, good week to get your paper done, okay? First test, I've got 1, 2, 3, 4 done, turned in. That is just under half of the class, so please get those in. Test 2, you've gotten yet or not?
We just got it recently.
Just got it, okay. So be working on that.
Still uncrumpled, so you know I haven't had to work.
Okay. All right. And then the other news is the bad news situation. Next week there's no classes. Get over it. Okay. Y'all get the whole week off. We don't. Okay. So what that does mean for you, the college is open next Monday, Tuesday, and Wednesday.
I may just have to come in here and sit in the classroom.
Yeah, well, do it. Okay. The college is open, so if you have business with the college, you can get that done, especially Monday, Tuesday, and Wednesday morning. I wouldn't hold a lot of faith in getting anything done Wednesday afternoon because people start disappearing, but also the administration quite often will call down and say, okay, y'all can leave after 2 or after noon or after something. So I wouldn't wait till do something till Wednesday afternoon. Yes? Uh-huh. Personally, that's what I was just going to say. What they usually do, see, they have professional meetings going on, but they're in Montgomery. I didn't want to go to Montgomery. And for those who don't go to the professional meetings, they have professional development on campus. And I haven't heard them say, but most of the time they have it on Birmingham campus. So the odds are, I can't swear this will be the case, the odds are Monday and Tuesday I'll be on Birmingham campus. More than likely the ACAT building, not even in my office. They may let us go Monday afternoon to work in our offices. If so, then I'll just stay on Birmingham campus. Now, if for some reason they have us out here, then I'll be out here. Same type thing. They usually have meetings Monday and Tuesday. Wednesday's a duty day, so I'll be on one of the other campuses. I just don't know which. If I've got things I need from here and just don't want to haul them around all weekend, I'll be coming out here Wednesday and work in my office here because that's where most of the materials are. But if I can get everything pretty much taken care of, and I'll probably have my laptop with me and stuff, I can work on Birmingham campus. It's a little closer to home, so I may be there. So what do you need? What were you thinking? Oh, turn your paper in? The buildings will be open Monday, Tuesday, and Wednesday. So if you come here, slide it under my door. Okay? If you go to the Birmingham, is that more convenient, Birmingham? Okay, you know where Dr. Pruitt's office is? Okay. Miss Rose Saxon is the secretary. Now, she might take all 3 days off because she usually cooks for a big family, you know. So, but if she's there, you can leave it with her and I'll pick it up whenever I see her, or just let me know and I'll go by there and pick it up. If that's more convenient for me. Oh, yeah, and you can do that because we'll still be in November. It's not going to gain or lose you any points, you know. So if you want to do that, you can. Probably, are you pretty close to Birmingham campus? Also, that wouldn't be an issue to run by the campus. Why don't you do this? The day you're thinking of doing it, or whenever you're thinking of doing it, call me at my office. Both the phone, same number in both campuses. If I'm in the office, I'll let you know and tell you which office I'm in, which campus I'm on, and then you can decide. And if you are going to drop it on Birmingham, see, it's no sweat at all for me to go by Birmingham on the way home and pick it up. So that won't be an issue either. So just give me a call before, if you think you're going to run it by, give me a call ahead of time. And if I'm not in the office, that means I'm not there. then maybe the best bet would then be email and say, I left it at Ms. Saxon's office, or I'll bring it next, whatever. If I know it's there, I'll just run by there on my way home and pick it up and have something great over the break. Okay, so whatever. So whatever's more convenient with you. But please let me, if you are going to leave it there, let me know so I'll know to pick it up. Because otherwise, I won't be, I can run by there Monday or Wednesday afternoon on my way home and pick it up then too. So just let me know. You don't even have to let me know until after we get back. But if you can, call or email. And then I'll know if I can get a chance, first opportunity to run by and pick it up. Yeah. Wish I could tell you something more definite, but I don't know where we're meeting and how long we're meeting and that kind of stuff. Okay. That said, otherwise, enjoy your Thanksgiving. Okay. And like I say, we'll be in meetings. I'll probably be in meetings on one of the two campuses, more than likely Birmingham, Monday and Tuesday, and more than likely one of my offices on Wednesday. And Victor's here. All right. Where we left off last time, we just had started 14.2, limits and continuity in several variables. Pretty much straightforward and not that far off from what you had in limits and continuity. I couldn't get the word out. In regular single variable calculus as opposed to multivariable calculus. Okay, as soon as this comes up, we'll be ready to go, unless you got a question. Did you find it?
I figured it out.
Oh, you did? Okay. Worth a look, huh? Okay. Any other questions before we get started today? All right, this is 14.2, somewhere around page 750, depending on which book you have. And as with anything, when you talk about derivatives, they talk about limits, okay? Because remember, a derivative is a limit, okay, in some nature, form, or another. So let's look at what we mean.
Even though we don't want it.
What's that?
Even though we might not want it.
Right, exactly. A limit. Assume that f of x, y, as some function in two variables, two independent variables, is defined near P, and P is somewhere in the xy plane, around the point AB. Okay, so your xy is somewhere around that point AB. Now, what we mean by the limit is the point xy approaches the point P. Xy is approaching AB, you might say, of that function f of x. If that has a limit, if the limit exists, that is going to be L. Okay? As xy approaches P, what is the functional value approaching? F of xy. Okay, then this means that for any epsilon greater than 0, and by the way, that measures changes on the function, okay, z you might say, greater than 0, there is going to be some delta, also greater than 0. Now, this so far looks just like it did, or almost just like it did, except there wasn't a y there, or a y there, okay, as it did in single variable calculus, that the absolute value of f of xy minus L, and remember this is some value on z, and this is some functional value at xy, that the difference between those is less than this value epsilon, okay? For all xy in the plane that's in some, and this is disk, remember? Disk around P and delta units from P, but the asterisk here means not necessarily P itself, okay? Because if it was P itself, then some of your differences there may actually be 0, and you usually want them to be some, they could be 0, but usually want them to be some of them, okay? So you see the only difference here was in single variable calculus, it'd be the absolute value of x, and delta is less than x be as x is approaching something, some point P, and single variable calculus as x is approaching some value, 0, 7, a, whatever it be, then the absolute value of x minus a would be less than delta. Now we say that the xy is within that disk around delta, disk around P, and within delta radius of that. That's what we're talking about here. Basically the same concept, but now you've got an area here, not just a linear variations in x. Okay? Was there a question? All right. Now, I know the slides are skipping over stuff. I don't want to skip too much. This, to me, is almost exactly what that second line was. Let's see where they're getting this from the book.
Example 1.
Okay, that's what I was trying to find. Is it in example 1? I think it must be.
It is right at the bottom of the page.
Right at the bottom. There it is. Yeah, there's equation 1. I see it. Okay, so let's do example 1 on this page. Show that, these are a couple very simple, well, let me get this, but fundamental limits that you need to know, okay? Show that A, the limit, as xy is approaching AB, okay, of x, y'all tell me, what do you reckon that might be? A, okay. This is the limit, basically saying as x is approaching A, of what is x? That limit had better be A, okay? And similarly, the B part is, ironically, the limit as xy is approaching the point AB of y, that's got to be approaching B. All right, those, as I said, almost seem trivially obvious, okay? And for some reason, this has been, but maybe it's just so small. But doesn't that look fuzzy, the lower part of that? Or is that, okay, to me it does. I look at this, I can hardly read it. Of course, it may be I'm getting clear off the board.
Once you blow it up.
Blow it up, it's fine. Okay.
It's so small already.
Yeah. Okay. Now, with that in mind, that's what we were supposed to show. Here is how we're going to show it, or at least a part of that. Well, I guess I'll need to do the other part first. Forget this for now. Okay. What we'll do is let P be this point AB, which, again, seems intuitively obvious. To verify the A part, we must show that for any epsilon greater than 0, you can find the delta. There is a delta, which is also some number greater than 0, such that, and that's what the such that is. Well, the first part, this is the second part of the such that. No, it's, well, let me write it in, because they're not quite the same, but close to it. Okay? That's the conclusion. Here's the if statement. If 0 is less than, oh boy, I don't think they've told you what this is yet, but you almost should tell by looking at it. They throw in a D of xy, comma, AB. Okay. Less than delta. Okay. Now, what that means the difference in. It's not quite derivative type difference, but almost. The difference between this point AB and XY and AB, that's what it means. The difference between this point and this point is less than delta. Okay? If you get, okay, it's got to be positive because delta will be greater than 0. So we're going, and distances are always positive, by definition. They're the square root of things, So that's positive. So as long as this distance between these two are between 0 and delta, greater than 0 but less than delta. Now, let's go back to what we were saying before. They don't want to actually equal to 0 necessarily. There could be, but you see, this asterisk here, that means excluding p. So therefore, they sort of rule out the 0 part. So that distance between xy and AB is less than 0. Then there is some epsilon greater than 0, such that, and I know this is hard to read here, the difference between f of xy and L, which here's your L, and here's your f of xy. So this is x minus a, is less than epsilon for all xy's that are within, this is element of, that's what, again, that to me is hard to read, that disk around P, here's P right here, the disk around P that's within the radius of delta. Okay. Now, and then the same goes with Y and B. If it's in there, if you're sufficiently close, which is that, no, given an epsilon, then you can get close enough so that this has to be true. Okay? That's all it's saying. You can get a delta small enough that that happens. See, that wouldn't be possible if you had some nice, smooth operating function here, except at one place it was way up here. Everywhere else it's down here somewhere. Well then, no matter how small you got your delta down there on the xy plane, you couldn't get within a small epsilon here because this value is way out of line. Well, that would happen if you have a discontinuous function. With a smooth continuous function, this will be the case. Okay? That's kind of basically what they're saying. Look at that as obviously. I mean, if xy is going to AB, then x is going to A. If xy is going to AB, y is going to B. Duh. I mean, why spend much time on it, but they do. I did. Okay. So, here is the picture that my arm waving was trying to illustrate. Okay? So let's see it better in pictures. I can't get but 2 of these on the screen at once. So let's do the best we can with that. Okay. In single variable calculus, where you have one independent variable, one dependent variable, this is a review. As x is approaching a down here within some delta, and that's what this region is on either side of a, within that delta there, then the function is approaching the limit L, and it's within some epsilon here of L. So for any epsilon you happen to choose, you can get a delta close enough there that you can get within the epsilon. That's what it's saying in single variable calculus. Now, the key here, what we were doing before, doesn't have to actually be a value at x equal a, just that it's approaching that as x gets closer and closer to a. Okay? That's what it means to be a limit. Same thing over here, except now, 2 independent variables, the plane down here, p is some value ab, x is a and y is b. In these 2 variables, the p has to be approaching ab, but it isn't just this way or that way. It can be from an infinite number of directions. So that's a little bit of a difference here. Okay? But whichever way it goes, as x approaches a from one thing, or b approaches Okay, here's x approaching, no. Here's x approaching A, there's y approaching B, okay? Coming in that way, you're going there. But this, for the limit to exist, it can be coming from any direction here, and it still needs to go to that point AB, okay? So that's why we talk about some region around, the disk around, that's what the D stood for, the disk around AB. It may not actually include AB. Well, that may be a hole up there, okay? But that no matter where you're going, as these are approaching there, you're approaching that value there, whether that value actually exists or not. Okay. Second?
Doesn't make for a very good parachute.
Yeah, I was going to, I was afraid that's what you, I thought that might be what you said. Okay. That, yeah. Lets out a little air, especially if it's starting to rip there too. Okay. Now, here's the picture of the disk. Okay? And we call this a open disk, meaning the radius, the boundary isn't necessarily defined. That's okay. You're just somewhere inside that, not necessarily on the boundary, but inside that boundary, and the xy is approaching AB from any direction. Okay? And what that means is your f has to be within a certain, here's your f of xy, here's your limit right there, the L value, and that this is getting close to this anytime xy is getting close to B. That, what that means is coming in this way, it's not going way out here, coming in this way, it's going somewhere else, That can't happen. It has to be approaching this value no matter where, how you're coming in, as long as you're within this down here, okay? And within there, you're approaching that. You're fine. So the function value is within epsilon for any delta here that is the radius of this disk around the point AB. Now that doesn't look like a disk around the radius, but that's what it says, open disk of radius delta. Seems like they could have drawn a much better centered disk than that. Okay, but that's what it means. And when they put the disk, that D star, that means it may not actually have a value here, that may be an open circle here, but still the function's approaching that one value.
They centered it in the new book.
Oh, they did, okay. That must have been left over from the old book. All right. Now, next we have the limit. Oh, no, okay, I guess this is next. Okay, here's another way to look at it. Well, let's maybe blow it up so maybe you can see it better. All right. Is this actually a problem? I don't see that it is. This is the one with x approaching A and y approaching B, I think. Okay. Oh, this is the y approaching B part. Okay. There's nothing in the problem said this was going to be a plane that I could tell, but if it is a plane, it still works. So here's the. It could work for x approaching A, but it also could work for y approaching B. So this is showing this. If you choose an xy somewhere in this down here within delta distance of the point AB, P, and that's what this means. The disk around P of radius delta, that's the point P, AB there, and the asterisk means it may not include the point P, but anything around P. Now this shows that it does have a value there. It's not an open circle there, but it doesn't have to have. That's what this is telling, the asterisk is telling. So up here, your f of xy has to be approaching y as this is a different problem. F of xy equal y. That wasn't part of the first problem. And they have the figure here, but I don't see where that is in the book. I guess they just threw it in here.
Well, they said, in the A part, they let f of x, y equal.
Oh yeah,
x,
yeah, that's right. As
and then
the B part is f of
x, y equal y. Yes, and then L equal B. I'm not sure.
it's the second part. As f of x, y is approaching y. So yeah. So this works. And by the way, this is exactly what this is doing here. Your f of x, y is your z value, and your y value is here. So basically this plane is bisecting the yz plane here exactly. It doesn't care what x is doing. That doesn't matter here. But for any y here, the z has that same value. Okay? So that's why it's this plane. They have to give it a little tilt so you can tell it's a plane. That's what you're talking about here. They have this parallel to the x-axis. It should be aiming down toward the origin here. It doesn't look like it is, but we'll hope that it really is heading that way. Okay. So the f of x, y minus b, the absolute value between f of x, y, that's that value. No, I'm sorry, f of x, y. X, y at some point in here. Pick a point. It has to be within the disk. Pick a point, and then it's going to be somewhere up there. The f of x, y minus b, the difference of this value here and b, is less than epsilon, but epsilon corresponds to that delta down here that makes the disk radius here. Projected up here, then your epsilon is guaranteed to be within that. That is always between that if y minus b is within delta units. So y could be here, 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 here. The y minus b is within delta units. Now that's true for delta x. What epsilon would you have there if delta was equal to epsilon? Okay? Because this is y is equal to z, basically, then your delta would equal to epsilon. Therefore, the limit as xy approaches ab of y would have to be b. Same thing we saw just.
And it's because y equals z.
Yeah, it's exactly it. Because your y is f of x. Your y is how far you are here. Your z, which is f of x, y, is that y. So, yeah, it's got to be the same. Limits seem circular sometimes in their logic, but they have great significance in meaning. What's that?
Type fit.
Okay. Here are your limit laws. These are the same limit laws you saw before in single variable calculus, just stated again in multivariable calculus. Assume that as your independent variables x, y are approaching some point p, call it a, b, or whatever you want to call it, the limit of that function f of x, y as x, y is approaching point p, a, b, and we're also assuming the limit of g of x, y as x, y approaches p, that both of those limits do exist. That's all that's required. The two limits exist as you're approaching that point p. Okay? The sum law then says the limit of the sum of two functions is the sum of the limits of those two functions. And we know these limits exist, so the sum of the limit of the sums exists. Okay? Constant multiple law. Okay? Looks like linear algebra, doesn't it? Okay? For any number k, some constant k, for any real number k, the limit as xy is approaching p, that could be point a, b, k times f of xy, that's the same. The limit of a scalar times a function is the scalar times the limit of that function. Okay? With the same limit sum. The product law. Okay? And the sum law, the product law, same way. As xy is approaching p, the limit as the product of two functions is the product of the limits of those two functions, which we already know exist. So this limit has to exist too. And what it exists as, the product of those limits. The quotient law. Notice they didn't have a subtraction law. All you have to do is put a minus sign here and a minus sign there. It's the same as addition, only you add the opposite. Okay? Quotient law, the limit is x, y approaches b. As long as your denominator is not equal to 0 anywhere within that disk around p. Can't be 0 anywhere there. As long as it isn't, then the limit of the quotient is the quotient of the limits. And we know those exist. And we also have to know that this one can never equal 0 within that disk. Okay? Just like you would expect them to be. All right? That was the limit laws. Now, the second part of this was continuity. Here's your continuity definition. And it's really not too far off from continuity in single variable calculus either. A function f of y, xy, now it has two independent variables, is continuous at some point p, a, b, if the limit as xy approaches a, b of f of xy has got to be f of a, b. It couldn't be that the limit from everywhere is approaching this value down here, but the actual value is up here, or down there, or somewhere else. To be continuous, that means whatever those are approaching, it is that value, f of a, b. Okay? We say that f is continuous if it is continuous at every point a, b in its domain. I would say at every point, at each point a, b. Whatever a, b you choose in the domain, it's always continuous there. Okay. Good deal. Now, single variable calculus is pretty predictable this way. However, with multivariable, you can get some strange things that go on sometime. Okay? And I think this is one example of strangeness. Well, maybe or maybe not. I don't see any problem here. Okay. Here's a graph. F of xy is equal to 3x plus y over x squared plus y squared plus 1. Okay.
Yeah, that's example 2.
What's that?
That's example 2.
Example 2. Okay, great. But it says evaluate the limits by, okay. We're evaluating the limit of this. This one's going to work out fine. That's what I was looking at and saying, I don't see any problems here. Okay? And where was I looking for problems? Did anyone read my sick mind and see what it was?
Maybe a cusp or something.
What's that?
Cusp or something.
What's it?
Like a cusp or something.
Yeah. And anything here to suggest that might happen.
Really deep trim checkers.
Okay, it looks like there's a deep hole there. Yeah. But guess what? Look at the function. What I would look for, and what I was looking for, making sure that denominator can't be 0 anywhere. Can it? No, because x squared is always non-negative, y squared is always non-negative. Add two non-negatives together, you get a non-negative. Add one to it, you can't even get a 0. It's going to be positive. Okay? So you can't have 0 down there. But there's no other things. Other things to look for: square roots, don't have any. Logs, don't have any. So it looks like everything's copacetic here. There shouldn't be any problems anywhere. Okay? Now, just because the denominator's always positive, that doesn't mean the function's always positive. It doesn't. Because, and that was the other thing I was looking for, it's certainly negative. Say when x is negative and y is 0 or very small. Okay, that's going to be negative. So on the x-axis, there's certain values where it's negative, and nothing really is showing up too clearly here. They look like these are actually very positive values here. So it seems like maybe they got the axes reversed, x and y. This should be positive x and that positive y, but we won't go there yet. But it looks like it's going to be fine. So let's see what they told us to do. Show that this function is continuous in figure 4 then a value. Okay, how do you show it's continuous? Well, basically what I was just saying. There are no places where the value can't be calculated, right? Put in a value for x and y, you can calculate it's going to come up a reasonable, non-explosive, there's no places it's getting infinitely large, infinitely small, disappearing, or anything else. So yeah, it is continuous. For all points on there, you can evaluate. The second part says, then evaluate the limit of this function. Let me get my, sorry. Okay. The limit, I lost, there it is. The limit of fy, and I'm going to put what fy is, 3x plus y over x squared plus y squared plus 1 as xy is approaching the point 1, 2. What would be that limit? Okay, 3 times 1 is 3, plus 2 is 5 over, and 1 squared is 1, plus 4, plus 1, that would be 5, 6, absolutely. Okay, pick any point in the world, any x, y value ever, any real number, you can calculate them just like we did that. Okay? Now, and I don't know whether you realize it or not, but you actually used one of the limit laws there, didn't you? The limit of this is 5, the limit of that is 6, as this approaches the same thing, and the limit of the quotient is the quotient of the limits. So without even thinking about it, you use the limit law. Okay, good deal. Now, example 3, a product function. Okay? Now, I don't think we have a graph of this one, so we'll do this on the same picture, it's just we're not using the picture. Okay. Example 3, evaluate the limit as xy approaches 3, 0, of x cubed sine y over y. Okay? Now, this one, you have to be a little more intentional about your limit laws. This is the same as the limit as xy approaches 3, 0 of x cubed times the limit as xy approaches 3, 0 of sine y over y. Okay? Do you buy that? Limit of a product is a product of the limits. Okay. Let me see if you should be buying that. Okay? That is okay to do as long as the limit of the f of xy and g of xy both exist. No question this one exists. Is there a question on whether that exists?
Yeah.
Why?
Y is 0, that's going to throw some issues, isn't it?
Yeah, but what do you have then?
Then we can determine.
Indeterminate form, because you have 0 over 0.
Then
Okay. Then what? Just because
we
it's
can
in the...
continue.
Huh?
We can continue.
We can continue, exactly, okay. And how could we continue? See, you've taken it out of two-dimensional and now made it single variable, okay? Because this is just as x is approaching 3, that approaches 27. Okay, so this part is approaching 27. No issue there at all. Over here, though, there's no x's, so it's just as y approaches 0 of sine y over y. Now, I was hoping one of you say, "Oh, I remember that from Cal 1." Okay, but that was so long ago. I wasn't really anticipating that. But what we could do, and I think we should remember this one, does the name L'Hôpital ring a bell? Oh, no. Okay, that too, huh? What could we do on an indeterminate form? When we determined that was indeterminate, in other words, it was a 0 over 0, we can proceed, like you said. And one way to proceed, if you didn't remember what this was, then you can at least remember L'Hôpital's rule, can't you? How does that work? Take the first derivative of the numerator and the denominator. And that would be the same as the limit. And now we'll just deal with y. As y approaches 0 of, okay? Yeah, and that would be what you say? Cosine y over 1. And what's the limit as y approaches 0 of cosine y? 1. So that is 1. Now, back in the day, when you were in Cal 1, this was an important thing because I hope maybe you remember, there was a graph that went like this, and as x approached 0, sine x over x is approaching 1. So, in other words, they were approaching 1 at almost the same speed, approaching 0 at the same speed, so their slope did. That's what L'Hôpital's rule tells you. All right. Now, did they do it using L'Hôpital's rule? I doubt it. Let's see. No, they just said the limit as y approaches 0 of sine y over y is 1. You should have remembered that. Okay? All right. They didn't quite say it in that tone, though. Okay. Now, composition is another important way to build functions, besides adding, subtracting, multiplying, and dividing, multiplying by constants, that kind of stuff. Composition. So here's theorem 2, which is composition of continuous functions is continuous. That's the title of it, and we'll word it completely as soon as I can get it done. Okay. Basically, the title says it all. The composite of continuous functions is continuous. So if f of x, y is continuous at some point a, b, and g of u, single variable function here, g of u is continuous at the point c is equal to f of ab. Well, where did that c come from? Well, we'll get it sort of in a minute. Why didn't they call this u here or call this c there? I don't know. That's what it's getting at. Then the composite function of g of f of x, y is continuous to AB, if those other two are, because the g of f, if f of xy, remember, is continuous at AB, and let's just say the value is either, let's say it's equal, there it is, c is f of AB, okay, and g is continuous there, okay, so then g of c is continuous as well. That's all it's saying. The composite of two continuous functions is also continuous. F of x, y is continuous. G of any variable, they just threw in a u there, is continuous. At AB, or, well, continuous here, then g of f of x, y is also continuous. Okay. Now, a counter example. Here is a rendition of some values of this function. F of xy is equal to x squared over x squared plus y squared. Doesn't look too far from the one we had before, does it? One major difference. The other one's x squared plus y squared plus 1. Big difference. Why? That denominator can be 0. And it can be 0 at places that the numerator is not 0. Okay? Certainly, certainly, no, it would have to be, numerator have to be 0 there too. X squared plus y squared, it is 0 at 0, 0. Okay? And certainly the numerator is 0 at 0, 0. So this looks like it might be indeterminate there, but let's plot a few values here. Okay? When this is the scale for your y's here, and this is the scale for the x's here. Strange place to put them, but that's what that means. Okay? Now, as you evaluate that function, say at the point x equal 0.1, y is equal to 0.1, there would be its value. Let's say that would be 0.1 squared, which would be 0.01, divided by 0.01 plus 0.01 is 0.02, and 0.01 divided by 0.02 is sure enough 0.5. Okay? And you can go and do lots of values here. Well, for instance, everywhere x is 0, except here, we're not going to mess with that yet, this is going to be 0. Okay, for any y is not equal to 0, this is 0, that's 0. Okay? But when y's are equal to 0, but x's aren't equal to 0, we won't include that case, then you have x squared over x squared, which is always 1. Okay? And then we just pick the value here that was 0.5. If we pick that one, it was 0.5, and that one, it was 0.5, and that one, and actually coming down this diagonal, and that diagonal, and this diagonal, and that diagonal is 0.5. Okay? Well, look at what we've got here. The limit as f of x approaches 0, 0 from the x-axis looks to be 1, from the left or from the right. From the y-axis, it appears to be 0, from the left or the right. From your main diagonal, left or right, or the other diagonal left or right, it seems to be 0.5. What's the limit of that function as xy approaches 0? Doesn't have any. Okay? It's not 0. It looks like it could be, but it's not. It's 1 from another direction. It's 0.5 from 2 other directions, or 4 other directions. It doesn't have a limit at x equals 0. Even though it's indeterminate there.
That would be indeterminate.
That's indeterminate, but this one doesn't have. Yeah. All indeterminates don't guarantee to have values. This one does not.
That would be 2x over 2x plus 2.
Okay, yeah, but that's using L'Hopital's rule in 2 dimensions that we haven't verified yet. But since you started it, let's see what would happen. That would be, if you could do that, which is not defined yet, we really can't, but that would be approaching 0, 0, you'd still be indeterminate in the first derivative. You get it again, it would be 2 over 4, which would be 1/2, which gives you these, but it doesn't guarantee the others. But we weren't taking derivatives right anyway. We haven't figured out how to do that yet. So, and in fact, L'Hopital's rule isn't defined for that case. When you can separate it out to single variable, it is defined. Multivariable, don't think it ever is, but I can't say that for sure. Okay, and by the way, what we're doing is example 5. We skipped example 4, didn't we? Sorry about that. I didn't see example 4. Let's go back and do example 4. Write h of xy, I'm writing it, okay, is equal to e to the minus x squared plus 2y as a composite function, and then evaluate the limit as xy approaches 1, 2 of h of xy. I'm going to write it e to the minus x squared plus 2y. Okay? Now, it says first write that first one as a composite of 2 functions. What would be your 2 functions? Give me an f and a g, I think it was. Okay? For some reason I made the G capital, but whatever. What's your F of XY? Negative x squared plus 2y. I'd be tempted to write as 2y minus x squared, but it doesn't matter. What was your G? And we're going to make up a new variable u, okay? What would it be? E to the u, okay? So our composite function h of xy would be g of f of xy. Okay? You buy that? Yeah, that's exactly what it is. Okay? Now, let's take the limit. Do you have to break it down into composite? No, you're going to do it anyway, but you don't have to. What do? That would be e to the minus 1 plus 4, which is e to the 3. And that's just some number. You can pull out your calculator and see what e cubed is. That's it. Okay? Now, wait, did we do the composite? Yes, you did. You first evaluated the f at xy, and then you took e of it. That's exactly what you did, without stopping and saying, oh, I'm doing a composite function here. You did it without really having to worry about it.
Yes, the more complicated functions that actually comes in handy.
Yeah, definitely. And then when we start taking derivatives and stuff, it really comes in handy. Okay. So let's see if that's what they got. I believe it is. Good for them. All right. Then going to this one. This is the one showing that a limit does not exist. And this was the limit we're looking for, the limit of this function of x squared over x squared plus y squared as xy approaches 0, 0. Obviously, it's an indeterminate form. It says examine it numerically. They did it for us. Thank you very much. Okay? And what you would expect is that and they actually colored in, they bolded here, but you see as xy approaches 0, 0 from that direction, the limit is 0.5. As it approaches from this direction, it's 1. From that direction, 0. From this direction, 0.5. From this direction, 0.5. From this direction, 1. From this direction, 0. From this direction, 0.5. It has a limit, different limits from different directions, all approaching 0, 0. That limit cannot possibly exist. Now, you might also say, it's hard to tell now, approaching from this direction, it's 0.8. From this direction, it's 0.8. From this direction, it's 0.2. From that direction, 0.2. From this direction, 0.8. Whoops, yeah. From this direction, 0.8. From this direction, 0.2. So it has a lot of different limits. Oh, one more here. From this direction, 0.2. Okay? And if we put enough points in there and spread them out more, every different direction you would be coming from would be some various thing. Notice this is going from 0, and there's somewhere place up there, somewhere about there. This one would be approaching 0.1, 0.2. There's some place that's coming in here. It'd be 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 0.9, 0.8. You know, if you had a big enough spread, you know, and made big enough divisions here, you would see that every different direction is coming in at a different number. Repeating them as it goes around, but it's going from 0 to 1, 1 to 0, 0 to 1, 1 to 0, and every value in between. And those are just the the tenths. We could do 0.11. Yeah, yeah. Okay. Now, and they show two methods. The first just is the coordinate axes showing those are different limits. Those are easy. And then they show it coming in at any angle. Y is equal to mx. Then you're going to have a different limit at every different m that you have. So that's going to be 2. Then there's a third method. Convert to polar coordinates. Yes, why didn't I think of that? Okay.
Not because you try to stay away from them.
No, not at all. Okay. And that actually is sort of interesting. They don't do it on the slide, I don't think. Let me see if they do. No, they don't. But that is interesting, since in polar coordinates, x is equal to r what? Remember? Cosine theta. Okay, and y is equal to r sine theta. Okay, so x squared would be r squared cosine squared theta, and y squared would be r squared sine squared theta. Okay, and the numerator here would be r squared cosine squared theta, and the denominator would be the sum of these two, which would be r squared times sine squared theta plus cosine squared theta, which is 1. So that's 1. So your r's divide out, and this would just be the values of that f of r theta, same function, but in r and theta, just would be cosine squared theta. Okay? Now, and as theta approaches, as r approaches 0, which is what you would be having, as the xy approaches 0, theta is not changing at all, but r is approaching 0. Well, as r approaches 0, you come in from here, and you have a value of 1. You come in from here, you have a value not 1. So all of those are different. You come in from here, your value is 0. So you get the same grid here. It's just that as r approaches 0, your thetas are different values as you come in different rates. So obviously that's not the same. All right, now I guess we're ready for example 6. Let's blow it up and look at it first. Boom. Okay. Calculate the limit as xy approaches 0, 0 of f of xy, where f of xy is defined for xy not equal 0, 0 as, this is the same function we were looking at. This is different from the one in this text. Basically, this figure 5 is another, that's the figure 5 from the previous page. Sorry, I didn't notice that. And what we were saying before, as you approach, and this is what I was pointing out too, C is equal to 0 there, 1.1, 0.3, 0.5, 0.7, 0.9. Somewhere in between here you got a 0.2, 0.4. You had other values in here too, 0.6 or 0.8. Every ray comes in at a different value, okay? But they start repeating themselves between 0 and 1, okay? Sorry. This is the one for this function here. This is example, I'm on the wrong page, 6. Calculate the limit as y approaches 0, 0 of this f of xy. So let me blow it up to begin with. Boom. Okay. As x approaches 0, 0. Now notice here, they have a hole there, don't they? Now the hole doesn't necessarily mean anything. The reason they put it here is f is not defined at 0, 0. Because obviously, the numerator would be 0, and the denominator would be 0 plus 0, which is 0. So that function is not defined at x, y equals 0, 0. So they have to put a hole in this one. That's not just by choice. It actually is one. Okay. Now, is this like the last one? No, in some sense it is. But it's not quite the same because you have an x, y in the numerator, x and a y in the numerator. Before you just had x's. They were x squared. So, for the life of me, it looks like to me okay, yeah.
Someone dropped their napkin.
What's that?
Someone dropped their napkin.
Someone dropped it. Oh, yeah, okay, it's floating through the floor. Okay, what I was looking at, and I wasn't quite seeing until I realized that y is equal to 0, which is along the x-axis. The functional value is and except for x equals 0, then, I'm sorry, except for, yeah, x equals 0, then this would be 0 over some positive number, except for x is equal to 0. But everywhere else it would be 0 over a positive number, which would be 0. Same thing true for when x equals 0, your and y varies. This would also be indeterminate, but anywhere that y wasn't 0, then this would be positive and that would be 0. So that would be 0 everywhere, except for 0, 0. So this is 0 everywhere, here's 0 everywhere, there's 0 everywhere, there's 0 everywhere. Now, what's the difference here is once x is negative, the whole function's negative, except along the x-axis. And there it's 0, because their y is 0 also. So it's negative here and negative there. Can't be positive anywhere else. It's 0 along all the axis lines, but it's going down on this side and coming up on this side. Positive everywhere over here, except 0 along the x-axis and undetermined. Okay? So that's what this one's looking like. And sure enough, this looks like this could be, it's not continuous function because it's not defined at the origin. But it is, what are we looking for here? You can define it. It is defined everywhere except 0, 0. Okay? So, and that's what the limit allows, as long it doesn't have to be there. Okay. Now, it says calculate the limit of this where f of xy is defined by that function. Okay? Now, it's easier to prove it's not sometimes than to prove that it is. Okay? So, again, they suggest let's go to polar coordinates. And if we do that, then this function f, and we're going to have to shrink it back again, would be, okay, we already got a pen, so I don't need that. Okay. Remember, x equal r cosine theta, and y is equal to r sine theta, and x squared would be r squared cosine squared theta, and y squared would be r squared sine squared theta. So now we would have r cosine theta times r squared sine squared theta over, which is, yeah, r squared, right? Okay? And we can very easily get rid of those r squareds. Okay? And now what we have is your f of r theta, which we're now not xy anymore, is equal to r cosine theta sine squared theta. Okay? Now, what's the limit of that as r approaches 0? That would certainly be 0. Okay? Because, doesn't matter what, thetas are doing, r is going to 0. And sure enough, that looks like the case here too. It's 0 here, 0 there, 0 there, and 0 there. Also 0 here, and here, and here, and here, and here, and here. Every way you're coming in, you're going downhill to get the zeros here, downhill there, uphill here to get the 0, uphill there to get the 0, and you're, yeah, that's what you got. The floating napkin. Okay. And it says, note in the last two examples we've used polar coordinates to first, why have they got a comma in there? I don't know. To first prove that a limit does not exist, and second, I guess that's it, prove that a limit does exist. One might conclude that polar coordinates might always be applied. Unfortunately, that's not the case. They can only be worked if we're taking a limit as xy approaches 0, 0. Further, they are mainly situations for which there are many situations where they will not work to prove either existence or non-existence. Okay, so don't always count on them. So let's see, do they have an example 7 slide? No, they don't. So we're going to have to do example 7 here. Erasing all ink. Determine whether or not the following limit exists. Here's the limit as xy approaches 0, 0. Of x squared y over x fourth plus y squared. Okay? All right. Now, they don't even give us a picture here, so we're going to have to just do some head scratching on our own. And as from their earlier suggestion, you might say, I don't think polar coordinates are going to help us here. Okay? Though it is going to 0, 0, and that would be as r approaches 0. Let's just see. What would happen if we use polar coordinates? That would be r squared cosine squared theta times r sine theta. How did that become a theta? Okay, over r to the fourth cosine fourth theta times r squared sine squared theta. Okay? Oh, that's a plus.
XY squared for the numerator.
Example 7? I think you're on example 6. Example 7. Is that right? Okay, good. Yeah. But I thought maybe you're in an older edition of the book too, and that may be true. Okay, and that's a plus down here. Okay? Well, let's see what we can do here. I had written times and it is a plus, I realize that. This would be r cubed cosine squared theta sine theta over, factor out an r squared, and you have r squared times r squared cosine fourth theta plus sine squared theta. Okay? Well, I can see we lose that. All right? Now, here's where things sort of start falling apart. Okay? If you didn't have that r squared in part of the denominator there, that wouldn't be an awful thing. It would be r R would be approaching 0 everywhere. But because of the R squared down there, as R approaches 0, you got 1 over, it just doesn't work, okay? You basically have a 1 over R, 1 over 0. Part of that is going to explode.
R goes to 0?
As R goes to 0,
Then you have a 0 up top.
you have a 0 up top,
Sine
and you have
squared.
a 0 plus sine squared there. That may work. Well, no.
Being 1 over, or 0 over sine squared, 0.
Yeah, but so that's indeterminate at best. Okay. Depending on your theta, so I don't think.
So if it was sine squared theta, it went to 0. If it was 0, then it'd be indeterminate.
Yeah, indeterminate. But you see, the sine squared sometimes it's 0 and sometimes it's not 0. So you have a 0 over a sine squared, and depending on which, well, no, it would be 0 anywhere that sine squared wasn't 0, but it would not be indeterminate where sine is equals 0. So that would still be an issue, okay? But they use this second technique they used before. They called it the second method. The first method was just look at the coordinate planes that we use in the one. And if you just looked at the coordinate planes, when x is 0, you have 0 over y squared, okay, which is always 0, except for y is equal to 0. When y is 0, you have x squared over x to the fourth. No, I mean you have 0 over x to the fourth, which is always 0, except for x is 0. So there are still some indeterminate possibilities there, but it looks like that could maybe be 0 on the, and it would be on the x and y axes. I think you would be okay there. It just wouldn't be defined at 0, 0. Okay, so it might look something like this, but we don't know that for sure. So the second method, they use consider paths of the form y is equal to mx. Okay? In other words, you've got straight lines going through the 0, 0, 0 at different slopes. That's what you're considering. So that gets you off the coordinate axes, though they will still work, but it gets you, well, two of them will. But let's try that then. Then this would be the limit as x approaches 0, because you've lost your y, because that's mx, of x squared, or mx squared, mx cubed, right? Second? Is that right? Mx cubed. Over x to the fourth plus m squared x squared. Okay? Now, that would be, or is, mx cubed over x squared times x squared plus m squared. Do you buy that? And this goes out and leaves you just an x up there. So this would be mx over x squared plus m squared. Okay. What happens to that as x is approaching 0? Okay. Numerator is always 0. The denominator is always m squared. Okay. Second?
It's going to be a positive number.
Okay, a positive number. Okay. So as x is approaching 0, okay, a non-negative number, because m could be 0. So we still have an indeterminate form there, but with m was equal to 0, first m is equal to 0, you're at the line y is equal to 0, which is the x-axis here. Okay. Now this is not the graph of it, and at the x-axis there, I think we've already determined that you do get 0, 0 everywhere. Okay. So that's 0 on the x-axis, and that's the only place that we have a problem, except maybe when m is infinite, which would be coming down the y-axis. Okay? Infinite slope, that would be the straight line of the y-axis. But I think we also saw that when y is 0, but x is not, well, didn't we see anything there? It looks like that's still okay. So, if I'm not mistaken, no. Okay. We got the same thing. Okay. It looks like it's okay anywhere on the straight lines. But remember, you don't have to be straight lines. It can be anything coming in. So the next thing they try is y is equal to x squared. I forgot about that. That's just all the straight lines going in. It's still okay. Y is equal, the limit is 0. But what if y is equal to x squared? Now what would it be? If you're coming down a parabola into the, and do they put a, no, they just choose one parabola. You could put a x squared and you could have a bunch of different parabolas. But let's just do this one. And let's see what our thing would be. Then we'd have the limit. Again, as x approaches 0, because you've eliminated the y, and this would be x to the 4th over x 4th plus x squared. You're right. Okay? And what would that be?
Oh, that would be x squared over x squared plus 1.
Okay, x squared over x squared plus 1. If you factor the x squared out of every term there.
And that works.
Okay? What do you mean it works?
It's not indeterminate.
Okay, but we have, as x is on the x-axis, okay, if you're on the x-axis, x is going to 0, yeah, you're 0 everywhere, okay? On the y-axis, well, let's see. Yeah, there is no y, but that would be y over y plus 1, right?
Right.
And that would be 0 everywhere. So x and y axis like we determined before. But what if you're coming down at some other value there? Let's see. At x equal 1. Y is equal to 1, right? 1/2. So, okay.
It'll always give you a non-zero, non-negative number on the bottom.
Yeah, but they do that too. But so what here? Let me see.
They got 1/2 right there.
I know. Consider the path along the parabola. Then, did I do something wrong here?
Wait, let's see. Since this does not equal the limit we obtained when we approach along straight line.
Wait a minute. I think we didn't do that right. It's x 4th plus y squared, but y squared was, y is x squared. This is x to the 4th here. Sorry. We didn't do it right.
Oh, because it's x squared and then we got squared.
Yeah, okay. That would be x to the 4th. And yeah, that comes out being 1 over 2. Everywhere. But it can't be, okay? Not at 0, okay. So everywhere coming in, the limit coming in the parabola, your limit is 1/2 until you get to 0, 0, and then it's not defined. Everywhere else it's 0. When you did the slope part, when you did the axes part, when you did the polar coordinates part, there were places you just couldn't figure out what they were, but when you do it this way, it's coming in at 1/2.
So it doesn't, you can't
Yeah.
get the
So
zero, it's in the.
it can't be, it's not defined, because it's 0 coming, most places, but along that parabola is coming in at 1/2. And that doesn't work. Okay. Sorry about that. Just because we screwed it up there. Okay. Let's look at the, huh?
So we fixed the problem.
Yeah. We almost proved wrong. Okay. Let's do preliminary question number 1. What is the difference between D at PR and D star at PR? That's really an asterisk, but it's easier for me to draw a star. Okay? What's the difference in those two? Yeah, the first one is everything inside the disk, and those are usually closed disks, by the way. The second one is everything inside the disk itself, not necessarily at P. Yeah, you may have a hole at P.
One is more decorated.
Yes. Okay. And oops, this should be it here. This is what 14.2. It almost sounds like a cribbage score. Okay, those would be 15.2. Okay. The star or asterisk PR, and they put little p there, same on there, consists of all the points on the PR other than the P itself. Okay, that's exactly what we said. Now, number 2. Suppose the f of xy is continuous at 2, 3, and the f of 2y is equal to y cubed. Let me see if I can get this done. F of xy is continuous at 2, 3, and that f of 2y is y cubed as long as y is not equal to 3. What is the value f of 2, 3? Okay. If it's continuous there, then it would have to be what it would be everywhere else but there. So what did you say? 27? I agree. I agree. Let's see if they agree. They agree. Okay. 27. Good for them. All right. Good deal. Paper in. Excellent. What's that? Yeah, Monday week. Huh? After Thanksgiving, yeah. Huh? Monday week, yeah.
Okay.
All right, thank you. All righty. Jonathan, I'll count him here since he showed up, even though he didn't stay very long. Okay. I'm easy.
Even sit down.
All right. Think we got that one. Number 3. So, how are we doing on time? Huh? Yeah. Yeah, it was 27. Yeah. Say again? 10 minutes. We got plenty of time. Number 3. Suppose that q of xy is a function such that 1 over q of xy is continuous for all xy. Okay? Which of the following statements are true? A. Q of xy is continuous for all xy. By the way, I guess more than one could be, because which of them are true? It could be more than one. Q of xy is continuous for xy not equal 0, 0. Okay, I don't think those two could both be true. Okay. Well, they could be. Okay.
Well, no, because one contains 0, 0, and the other one would not.
Okay, but it doesn't say it's not continuous at 0, 0. It says it is continuous for all xy not equal 0, 0. That's really picky. I don't know if that's what they're meaning. Let's go on. Q of xy
Basically,
is not equal to 0.
one of them says that it's not continuous at 0, 0, and the other one says it is.
No, it doesn't say it's not continuous
I
there.
think that's
Right.
what they're implying.
It's what they may be implying to you. Okay. For I can't write, for all xy. Okay.
I mean, the C is going to have to be for sure.
Okay.
Because it has to be on.
Okay. Yes. C has to be true. Okay? Because it says Q of xy cannot equal 0 for all xy, because this says that Q of xy, that 1 over Q of xy is continuous for all xy. That means that denominator cannot equal 0. That for certain is true. I don't think you can necessarily.
I'm going to have to say that B.
What's that?
I think B would have to be the other one.
I think B could be, it certainly could be true. It could be true that it is continuous at 0, 0, 2, but we don't know that for sure. Okay? But we do know that Q of xy cannot equal 0, because that would negate what we have here. We know this is true. Okay? And Q of xy is continuous for all xy not equal to 0, 0. I think that's okay.
I know.
And we just can't say whether Q is continuous for all xy. If the denominator
Let's see. Yeah, it says all three statements are true.
okay.
So
It is.
they were being.
Right. A little picky.
I
Yeah.
don't.
Yeah.
Okay.
There's no reason that Q of xy. It's just we know that this has to be true. Q of xy can't be 0, but that doesn't mean it can't be continuous anywhere. Okay. It just can't be 0. It can be anywhere not 0, but it just can't. We know it can't be 0. Okay. So it's all three statements. I didn't go back and look. You did. Okay.
Yeah.
Let's look at 4. We're going to have to erase some to do 4. Suppose that f of x0 is equal to 3. That's a 3. Okay? For all x not equal 0. Okay, we'll buy that. And f of 0y is equal to 5 for all y not equal to 0. Okay? What can you conclude about the limit as xy approaches 0, 0? F of xy. I believe you have to conclude that, okay? Because if the first is true, for all x's not equal to 0, that means for all, let's use this, coming here down the x-axis, and not just the x, oh yeah, that's what it's saying. X-axis for y is equal to 0 is 3 everywhere there, except at 0, okay? X equals 0, okay? But coming up the y-axis is 5 from every direction on the y-axis.
And
Is
they're
5.
not converging on the same
Yeah,
plane.
they're converging on 5 up here and 3 down there. Ain't gonna happen, okay? So that's gonna be what can you say about the limit doesn't exist? I think your statement is right. Does not exist, okay? Good deal. Homework exercises here in 14.2. Any of the odds 1 through 7. Either 9 or 11 or both. Any of the odds 13 through 17. Any of the odds 19, either 19 or 21 or both. Do number 23. Now we did do the squeeze theorem here, but it works a lot like it did before. So 25, try to do 25. Any of the odds 27 to 39. And either 41 or 43. The 43 says it's mostly a writing thing. Okay, here is the main thing we're doing in chapter 14 is 14.3 partial derivatives. This is the meat. Everything else has been fluff leading up to the meat. This is the meat. How much time we got? 2 minutes. All right. I doubt if it's going to load in 2 minutes, but let me see. Well, I should have done this first. Okay, I'd already done it, but it's fine. Okay. 14.3. Let's see if we can get it loaded quickly. You hear me? No, it's not listening. It's like a student, okay? There it comes, okay. I just was kidding, okay. PowerPoint is so fast. Just amazes me. We're still loading. About 1 minute? Is that right?
Yeah, about one.
About 1. But what I was saying before, this is the most important section in the chapter, I think, or the most crucial in the chapter, maybe not most important. And then the others build on this. Everything before here was just kind of the stuff they have to go over first. And I don't know if it's going to load in a minute. This is amazing. We may be starting at 14.3.
We'll have a full dose next time of the section. Be sure to really cover it.
You promise, okay. All right. Did everybody get the second test? Okay, good deal. All right. Oh, you didn't? Okay. I couldn't remember.
All right.
It's still trying to load. Well, we still got part of a minute. Okay. Okay. That's your second test, isn't it? I want to make sure I'm giving them the right one.
Yeah.
Okay, good. That's good deal.
Did the first couple of them, so I recognize those.
Yeah. Well, I guess this isn't going to do anything. So you're going on to Scholar Bowl. And what I will do is try to work up the rest of those numbers, but I also have to,
Richards.
I know, that's what I was going to say. I also have to do his and start looking at yours, but yours is crucial on time-wise. Okay.
If you did it by next week, I'm sure they'd be thrilled.
Okay. Well, what I'm hoping to do is get it done Friday on the Birmingham campus, but his can't wait till then.
Right.
Is that right?
It's
Okay.
due
Today. Okay.
And I'm sure he sent you some kind of email or something with or whatever. I'm not sure.
Yeah. Well, I'll see what I got on there. So, but I need to get out of this first. It is now 10:55. I think I'm going to. 1:55. I'm going to cancel.
Anyway, I'm gonna run down here.
Okay.
We should be over by 3:30.
Okay. I will.
Half of them have a Spanish class that starts at 3:30.
Okay, on this campus or the other?
Here.
That's okay. That's good.
But anyway, so
Y'all are starting at 2. Okay.
right away.
I swear, this is hung up. I'm going to do my other. Do you need to get in the office? You want to leave your bag?
No, I'll get them.
Okay. Because I want to get my YouTubes and everything straightened out, so
All right.
I'll be here for a bit.
I need to talk to you for 5 minutes.
Okay. Yeah, let me turn this off. I also need to turn off my computer's acting like it's hung up. It's still acting like it's hung up. So I'm going to wait. It's not what I wanted to do.